Okay, good morning, everybody. How's everybody this morning? I know. So hopefully I'm not going to make it too overly intense. So I've tried to make sure we focus primarily on parallel computing with respect to the problem. So I'm not planning to throw anything nasty at you today. So anyways, as we've heard here, I'm going to be talking about a parallel algorithm that is used primarily in theoretical computer science. Now, it's under the intersection between combinatorial optimization and combinatorial enumeration. Now, those two things have relationships with one another. One often focuses on search problems. The other one looks at generating objects based on combinatorial descriptions. So, for example, a graph is one such object, among many others. So, if you're wondering, if you're curious about where all this content could be found, you're curious, I'm going to be talking about a sequential algorithm, then moving into a parallel algorithm. They can be located in these two particular papers. So what am I exactly going to talk about today? So the key thing I'm going to talk about is trying to integrate the ideas from the sequential computing aspects of generating these particular combinatorial objects, and I'll be walking you through some of these definitions. And believe it or not, they're relatively simple. But we want to also come from the parallel computing aspects here and combine those concepts together to try to make efficient algorithms that we can exhaust large numbers of elements that can be consistent with these objects. So I'll be talking about that, and then try to get some limitations on the sequential end and why we need to bring in parallel computing. And, of course, I'm going to be talking about some techniques. So some of these are actually going to be ones that are familiar to you, and just you may not know it yet. So it's going to be quite a lovely day here. Now, I'll be showing you a sequential algorithm I came up with in 2012 for generating a particular object called a second-order restricted weak integer composition. And I know it's a mouthful, but I'll be showing you that it's not just about, okay, I have a sequential algorithm, let's just make it, and just like throw loops on it and whatnot. It's a little bit more complicated than that. So I'll be showing you how to streamline such an algorithm, and then show you how you can make it nice and parallel. So keep in mind the architecture we're going to focus on is shared memory machines. So things like when you're talking about OpenMP and those are going to come into play here. So what exactly, I got to start with probably the most basic definition. The very first thing is a weak integer composition, or I call them weak compositions because we're talking about integers, so it's easy enough just to say weak composition. So what exactly is that? Very simple. It is just a set, and that set consists of n tuples, or just, you can think of them as arrays of length n. And if you were to add the numbers inside of each part of the sequence, it equals a number we call S, or the order of the composition. So we have the number of parts, which is n, and we have the sum, which is S. So the convention often used is that we indicate that with a C. Sometimes I see WC. And the sum will be indicated as the first subscript. So 4 in this example, and 3. So just very simple. So you can see that every single one of these triples here adds to 4, but there's 3 positions. Now the key thing to remember here is that a weak composition here allows the number 0 in the sequences. If you don't see weak in front of it, you just assume, oh, you're not allowed to use zeros. It has to be positive integers. So one thing I need to make sure we point out here is that these objects are massive, as you may suspect, because there's a lot of different ways I can arrange these objects. In fact, this is exponential. It's a very, very large number. So when we talk about largeness like in this, it can get overwhelming on the memory. So we'll have to keep that in mind. So just a picture to capture everything we're doing here. So an easier way to think about this object is any possible solution to anything of this form. So if I was only allowed to use positive integers and 0, I'm only allowed to put in them into n spots, and they have to add to s. Very simple. Very simple. So you can think of them as you're allowed to pick from a bin, and each one of these bins you're allowed to pick from 0 to s. So is that clear to everybody so far? This one should be pretty standard. So Now I want to talk about a particular problem. It's called trying to generate something called a restricted weak composition. Now, this is actually the main motivation for generating the objects I'm interested in. What you do is you just take any subset of a weak composition. That's all the definition is. So when I say restricted weak composition, it can mean like, if I go back here, I can say, okay, I only want that one, this one, that one, and that one. Maybe it corresponds to some description of an object that maybe I'm trying to prove a theorem about, or maybe I'm trying to go and exhaust these, so maybe some application, whether it be in computational linguistics, trying to break down dictionary and break down all those little pieces that form words, whether it be in cryptography generating keys, whether it be in software generating test cases. These can come up all over the place. So it's not just, okay, there's one application. Oh, if you can find a way of adding something, you'll find an application for it. So let's go back to here. So what exactly is the problem with trying to generate any subset? Well, if you try to generate a particular object, say if I were to generate this object. So remember, this is a set of n tuples. So if I wanted, say, 3 of them, and I already know how big this is going to be, do you think that if I only want 3 out of, I don't know, it could be a very large number, would you think that that's very efficient to do just by throwing them away? Probably not. Probably not. That could be very time-consuming, whether it be in sequential or in the parallel aspects. Because these could be millions upon millions of sequences. In practice, this could be billions. So that could be a lot of sequences. So it's not very efficient to prune them by just generating a weak composition and just throwing away things. You got to be a little more careful than that. So what the idea is, instead of thinking about, oh, I'm going to generate this whole weak composition, I'll find a class of compositions that fits the description I'm interested in, and then prune that. So why? Because it'll be a subset of that, so it may have a more accurate description of what I'm looking for. But I can prune a lot less items. So this is one of the main motivations here. So if we can try to make k as small as possible, so note that this is a lower bound. So you can't break this thing. So you just have to keep describing more restricted cases to get what you want. So let me just give you a couple examples of what these would look like. So, oh yeah, one thing I wanted to mention is everywhere I put a little reference up here for an author, that's the date an algorithm came out that was able to generate this object, whether it be sequential or parallel. So keep in mind, this is a very classic, if anybody have out there the art of programming, if you look for the Knuth-Klingberg gray code, this is the algorithm that I'm talking about. So if you have that book, go look it up, it's fun. But this is one that's actually made a bit of a spark in terms of research. Instead of just saying, oh, I'm going to exhaust all of them, now Walsh came up with a lovely result that's used a lot. In fact, you're able to get a weak composition, but you're allowed to restrict each position by a number. And by doing so, you can limit the size of these bins and pick from more restricted bins. So for example, here, this could be like a 3, and I'm allowed to do 0, 1, 2, and 3. Note, you always have at the bottom 0. So this is more restricted. I can describe what I want a little bit better. Now, this is where I'm going to kind of jump ahead. So note that there have been some results in this area, and they've been getting more and more restricted. They use certain techniques, which I'm going to talk about. Now, this is an example of a first-order restricted weak composition. So this is something I introduced in 2012. So what you do, you just simply define yourself a lovely subset. It can be anything. So now instead of having, oh, it's 0 up to a number, now it's anything. So anything between 0 and 1, of course, inclusively. So this could be 1s, this could be 3s, this could be 7s, whatever it may be. I throw it into each one of these. Note, in the first order restricted weak composition, all of these are the same. So that's pretty much the difference between this first order and what I would call the second order restricted weak composition. So in the second order restricted weak composition, all of these bins can be different. So this is very, very general. Now, to put in the perspective of the computational landscape, if you were to generate this object, this is no different than exhausting an instance of subset sum, which is NP hard or NP complete in its decision sense. But yeah, you can see that this can be really nasty to do. You could come up with a nice, clever algorithm to do it, but you may or may not find what you want. So you have to throw away what you'd like if you wanted to, say, solve subset sum with this. Okay. So are there any questions so far? I just want to make sure. So remember, just the key thing here is that we're just trying to find all the possible solutions to this little equation here, and I'm allowed to use numbers in certain bins. Yeah?
So just to make sure I understand the first order, it's instead of choosing 0, 1, 2, 3 up to some limit, you can now choose, I just give you n random numbers from the set. Okay.
Yeah, exactly. So when you give this out, when you start executing this algorithm, that's a part of the input. So you can think of this as like a two-dimensional array. So now I want to talk about some techniques here. So a very classic approach of doing this is there's another combinatorial object very well related to compositions called partitions. As the name would suggest, you just take an integer, you break it up into its pieces, and if they add up to that number, then you're okay. The one thing that makes the difference between an integer composition, or weak integer composition, and a weak integer partition is the order doesn't matter. So it has that permutation combination relationship. So this makes it a little easier. So notice that the sets are a lot smaller here. So it gets its kind of description, but notice that now I'm not permuting the elements inside of each one of these. So how do I exactly get a weak composition out of this? You just simply take permutations of each one of those when you're done. Now I bet you're saying, well, why would I want to do that if I already know I can't exhaust all of them? And if I want any one of these subsets, or heck, maybe if I want this object. Well, while you're permuting them, you can always check them, which makes it very lovely. Now, one thing I will point out, and a technique I'm going to show you, is something called a loopless algorithm. So with a loopless algorithm, what you do is you generate the objects, and then what you do is you give each one of these to a procedure that's able to generate each successive object in constant time. I know it sounds really weird, but it's really nasty. They're nasty to design, but they're very beautiful in implementation. So if anybody's interested in low-level machine implementations and they like using bit operators, this stuff comes up all the time. So if you want to get yourself a weak composition out of a partition, all you do is permute the elements. And note that 2008, they did come up with one for generating these using gray codes. So not that sequential here, but I'm going to come back to that. So what exactly is a loopless algorithm? So this is a class of algorithms that have a certain form. So the first thing is that, so let me just break down the structure here. So you have this object, say this, and I want to generate all the, say I want only the red ones, say maybe the partitions here. What, in a loopless algorithm, I'm allowed to generate the first object, whatever order it may be in linear time. So I'm allowed to take as much as linear time to generate that first object. Now, every other object, on the other hand, once I have the first one, I'm only allowed to fiddle around with that particular object I've just created, and I have to do it in a constant number of steps. So, one other thing to point out, you're not allowed to put more and more work in between each one of these. It has to be constant. So, big old 1. So that could be 5, that could be 20, whatever you like, as long as it's constant. So, a lot of the developments in these enumeration or generation algorithms is in something called loopless gray code algorithms. Now, anybody familiar with a gray code? Gray code is where you have a binary sequence and you make exactly one bit change in terms of, like, say if you're talking about gray code algorithms. If you have a binary sequence, you're only allowed to make one binary swap. Say one of these positions, change it from a 0 to a 1 or a 1 to a 0. Only allowed to do that once. So that's like a solid big theta of 1. And it's only 1. It's very, very efficient. If you can get one of these, you're effectively done if you're describing that particular combinatorial object. So These kind of algorithms are very, very easy to parallelize if you have something called an unranked function. Now, when you have any kind of combinatorial object, whether it be a data structure, whether it be a graph, whether it be anything I can describe using sets, you can often rank them if they're countable. So if I want to say take a given object, I can put them in a particular order, and if I have them in a specific way, I can try to find relationships between when I make one change to another change. So one of these bit operations. So if you put them in a particular order, you can rank them, say 1, 2, 3, 4, 5, all the way up to the size of that set. So if this were a graph, you can label each one of those vertices or each vertex. Whether it be in a linked list, you can take one of those nodes, label each one. The key thing here is if you get something called an unranked function, it takes that rank that you assigned, whether it be 1, whether it be 20, whether it be 30, and it transforms it into the object you're interested in. So sometimes you can't get this nicely. Now, there's one thing I will point out about that. You can make an unranked function very easily out of a loopless algorithm. You just simply give it the loopless algorithm. But in our definition, if we want to parallelize this, we'll see why we'd want this unranked function. If we don't have that, we would have to just use the whole algorithm again and again and again. If we were to parallelize this, say if I wanted to go from, okay, I want, say the first 20 sequences done on one processing element, and I want the remaining 20 on this other one. If I don't have one of these unranking functions that can be efficiently computed, so irrespective of generating the whole object, it's not very useful. So you have to think very carefully about how you're going to attack these particular kinds of combinatorial objects and parallelizing their given algorithm. So it gets a little more complicated with these guys because they're very, very simple algorithms. If I showed you one, you'd think, oh, I can implement that in like 10 seconds. They're really, really, really simple. Like, extremely simple. They're just usually a loop. And it's kind of ironic they call them loopless, but it has a loop in it. It's just because you're taking an object and you're producing constant time objects in succession. So let me just give you a simple example. This is probably the easiest thing I can think of, and this is something you probably have encountered maybe in first year. Very simple. If I want to print all of the odd integers, positive integers, less than or equal to a number, say n. Very simple algorithm here. I just start at 1, and I just add 2 to it every single time, and I print them out. One thing I will point out is that the print operation has nothing to do with the actual construction, so it's irrespective of this. So if you were to go take the time complexity, it would be the amount of complexity of the whole set that you're generating multiplied by n for the print statement. So whether it be a print statement, whether this be going into a data structure like a tree, a back tree, whatever it may be, the key thing is that this is doing nothing to the actual construction. This is, though. That's a constant step, right? So all I'm doing is each successive object, I'm doing it in constant time. This is a very, very simple algorithm for generating this, and this could represent a set of positive odd integers, less than or equal to n. Very simple. So this is loopless. Very simple. You get at most n steps to get the first object. Very simple. All it is just constant time. Then each one of these constant operations. So are there any questions about loopless algorithms so far?
Basically, an iterative algorithm.
Yeah.
Using whatever we did before.
Yeah, so all I'm saying here is that you build one object, then you use that object to build the next one, and you have to do it in constant number of steps. Yeah?
Would the Fibonacci sequence be done in a loopless?
Ah, that's a good question. I guess you could get away with that one. So if you're, say, doing dynamic programming, you probably could get away with that one just fine. So, yeah. So it can be a little, so the structure is very kind of vague. So as long as it's a constant number of steps to build each successive object. So it could be in a lot of different varieties. But traditionally, it's usually just one object, build the next one, and then this all just represents one set. So I want to talk about actual parallel generation techniques. So I've showed you a couple sequential methods. Now I'm just going to take them and throw them into the categories of how you would parallelize these things. So if you're wondering, you can find these particular techniques in that particular paper, and it kind of outlines them, but they're not that terribly complicated. Most of these you're actually very familiar with. So the very first technique, one that you're probably very familiar, you've probably done this before, where you take your problem, you cut it up into pieces, and you throw it to each processing element in kind of a load balanced manner. So this is probably one of the more, it's probably the easiest way of handling things. Pretty sure all of you have tried this before, where you just take your entire instance. Say if I want to generate, like, say if I'm talking about, let's think of something even simpler. Say if I have an array and I'm searching for an element. I could maybe give the first processing element, say if I'm trying to do a naive linear scan, maybe. I could give the first chunk to one processing element, one to the next, and they could each do their own search. So that's just this technique, except now we're just talking about combinatorial objects. So all you do is if you have n objects, the goal is just to break it up over the number of processors, or in our case, threads. So what we want to do is we want to use loopless algorithms. So I'm just going to give you one example of this, though the technique I'm going to use is the third one that I'm going to show you. So if you have yourself an unranked function, all you need to do is you need to generate at most n over k with a ceiling on it. So why? Because you break them up into chunks if you're able to determine a given object. So if you've assigned them some order, say lexicographic, alphabetical, whatever order it may be. So some of these algorithms do have these properties. But if you have a way of ranking them, if you have an ability to get back the object afterwards, all you do is you just say, okay, this one's going to do this many of them, this one's going to do this many of them, and all the way till the end. Say if I have like 8 threads, it would be processor 1, thread 1, thread 2, thread 3, all the way up to thread 8. And you can give them up their n over 8 objects to work on. And as long as you're able to index and construct that object for that given point, that's all you need. Because you could generate that, and if you could do it in linear time, then it's still a loopless algorithm. Except now it's parallelized. So now each one of those, if they take a linear time, then they have that constant succession, then it's a parallel loopless algorithm. So these are very natural to loopless algorithms if you have an unranked function that's efficient. So if you don't have an efficient one, it can be very, very hefty and costly. So advantage, of course, there's no communication between threads or processing elements, because all you have to do is just throw them on there, and they'll just do their own thing. They have everything that they need to process and construct the object's pieces. So this is very natural to do if you have this. The drawback, though, as the author here suggests, is this is not very good for very simple processing elements. The reason why is because these operations could be very, very costly. A good example is if I go back, like way back, right here. This one, just a weak composition. If you try to use Klingsberg's algorithm here, and there is an unranked function for this one, if you were to use that one, it has a hefty computational expense of computing a lot of choose functions and a lot of exponential functions, which can be very costly on a very simple processor. So it gets very, very complicated if you have very simple ones, so they have to be roughly on par with what you'd expect for a, say, a sequential computer. So you have to keep that in mind with this technique. So it has to be able to handle the computations you're going to throw at it. Say if I'm trying to generate all the possible subsets of a given, say, 1 to n, I would have to compute 2 to the n minus 1 at some point, because I want the size. So let me just apply that technique to that original problem I had. Now this is a lot more complicated than what I had before, and you can actually write a way more efficient parallel algorithm than this one for solving this very simple problem. So all I've done is I've applied the technique I've just described. So instead, now I have T here to indicate the number of threads or processing elements. And now I'm just going to do a technique that you're probably very familiar with. You just break it up into chunks. Now, I have this unranked function that tells me, now this one's really simple because all you need to do is find out In our case, this would be L, the Lth odd number. Very simple. So this is just a constant operation. And all you do is you just take a while loop and you generate that piece. So I bet you're wondering, well, why did I write it this complicated? I could easily just write this in a for loop and I'm done, right? You just go for and then, okay, I'll just go 2k plus 1 and I'll k going like this. And especially if I'm using OpenMP, I can go for parallel, nice and easy. But the reason why I show you this way is because loopless algorithms tend to be a lot more complicated than that. They usually take a form like this if you're able to come up with an unranked function. In fact, I almost actually took this one from the Klingsberg's parallel algorithm. All I did was I made it a lot simpler at the start, but the technique, you're very familiar with the idea. I take how much work I'm going to spread across them. I find out which index is the start. Let's think of it like the array example. If I were to search particular parts of the array, I break it up into chunks and I look at each chunk. No different, except now the data is dynamic. So I'm just building objects instead of finding things in my input. So that's the first technique. So this is, you could write a way better one and really fast. Now, the second technique, I'm not going to say that much about it because we're not going to focus that much on it, but it is something that people have looked at, is considering shared instances. So in this particular case, all you do, instead of looking at it, okay, I'm going to break my instance and I'm going to share how many I'm going to be constructing, instead I say, okay, I'm going to put each processing element or my thread in charge of each index of that, say, sequence. Say if this were my integer composition example, because each one's length n, I would just say, okay, processing element 1's in charge of position 1, 2, 3, and maybe, okay, now processing element 2 is in charge of 4, 5. The key thing here is now the processors are in charge of building parts of the object, not each piece of the object itself. So the way you can think about it is, technique 1 is generating them like this. You're generating the whole sequences together in groups. Technique 2, you're saying, okay, each processor's in charge of one position. So now they're generating like this. So they'll produce each part, and then they just put them all together at the end. Can anybody see what would be costly about doing that, though?
The communication?
Yeah, communication. The synchronization will be very hefty, especially if this is going to be a big object. So communication can be, it can really slow you down. Also think, imagine if this were, say, like 2 to the n minus 1 elements, for example. That would be a lot of objects. And imagine if I had to put them back together at the end, like the agglomeration phase. That would be really, it could be costly. But this technique works rather well on certain architectures. So particularly the SIMD architecture works extremely well. And if you're wondering, a particular case called the linear array, so it's just an array of processors, and they have at most 2 neighbors. So say if I have one processing element here, it's only able to communicate with its neighbors. So some people have looked into that particular object, and they've been able to develop parallel algorithms for things like integer composition, so not weak integer compositions, but one where it doesn't let you have the 0. Permutations, combinations, so there are existing parallel algorithms for some of these objects. So the third technique is a bit of both. I like to put a bit of both because it makes it nice and easy. What you do is you take elements of both and you try to see, hey, look, there's some things over here I could do well, like I want to maybe get rid of that communication issue, and maybe I want to have it so that I build some of the objects, but I don't necessarily want to break them entirely into groups. So sometimes it's difficult to only do one of these techniques. So for example, if I don't have an unranked function, it gets really difficult to do technique 1 unless you have something that's relatively easy to do. So oftentimes exhaustive algorithms, so these aren't loopless, they're just brute force exhaustions, tend to take this kind of caveat here. So what you do is you just take the algorithm and you're just going to break it up, and your job is just to, say, generate each object, but maybe you want to break it up into groups, but at the same time you may want to generate things simultaneously. So this tends to be a little bit more of a complicated problem here. And actually, our algorithm falls into technique 3. Why? Because there is no unranked function yet for the combinatorial object, the second order restricted weak integer composition. We don't have that yet. There is actually no loopless algorithm yet. And probably with my suspicions, there may not ever be one. Just because of the nature of how gray codes behave and the restrictions we have at hand here. So that's just one kind of thing to just keep in mind. So just let's get it out of the way. This is the problem we're interested in. I want to generate a second order restricted weak integer composition. Give it something called a restricted set, which is just each one of those bins that I talked about. Remember, each one can be different, so that's just how I'm denoting them. And yes, that is a pretty nasty looking symbol set there. Yeah, that's how I denote a second order restricted weak integer composition. It's a mouthful just like the symbol is. But the key thing here is just we're going to be looking at a parallel algorithm. So in 2012, I came up with a sequential combinatorial algorithm that attacks this problem. But oftentimes, sequential is not just enough. We need parallel computing because these instances can get rather large. They're very output sensitive. So let me give you an idea. So I'm going to be walking you through the sequential algorithm and kind of a bit of a step-by-step procedure. Then I'm going to take and modify it, fix it up, so that we can parallelize it. Then I'm going to show you how easy it is, after you've done so, to make a parallel algorithm. So how this algorithm behaves is it's an inductive algorithm. It's iterative. So it doesn't rely on, say, recursion or anything. A lot of these kind of naive solutions can infer recursive solutions, which can be really nasty on memory. In fact, one actually not that long ago, in 2010, was a recursive solution for the first order restricted weak integer composition. So how exactly does this work? What we're going to do is we're going to have some simple data structures. We're going to have queues. So remember, we can enter and leave sequences or elements from a queue. We're going to have S plus 1 of them. So starting from 0 all the way up to S. Remember, S is the sum of all the sequences. So not sum, I'm talking about the sum of the elements in the sequence. Now, how exactly are we going to take and move and copy these things? We're going to use an adjacency matrix. So yes, those are going to come up. So how exactly are we going to use them? So just hold your breath for this. I'm going to give you some explanation for each one of these. So this is just kind of get us set up here. So what exactly is one of the edges in this directed, well, you can think of it as a graph. Each one of these means that you're going to enter a sequence into an opposing queue, which is at that given position in the adjacency matrix. So there's going to be one queue that's going to be in charge of keeping all of the valid sequences. Because what we're going to do is we're going to generate our sequences inductively from left to right. So we're going to use technique 2, but with a bit of technique 1. So we're going to clump them up, but at the same time, we're going to build them from scratch. This way. So let me just give you an example of the inputs for this algorithm. You give it S, so that remember that's the sum. You have N, that's the length of the sequences. So in this example, note I've actually put it so that, yeah, each one of these is in sets, though it should be actually the other way around. That's a typo there. So notice, actually, no, that's fine. Never mind. I'm getting ahead of myself. That's the restricted set in form of an array. Actually, it's a 2D array here, if you were to implement this. So each one of these positions are each one of those bins. So for example, the first position is allowed to have a 0, 1, or 2, or 3. Likewise, say if I have position 3, it's allowed to have 0, 2, or 4. So remember back to that picture. So what exactly we're going to be doing here? Well, we're going to cover some of the major cases here. I'm going to quickly show you the trivial ones right in a bit. So how would this initially set up? Well, you set up 6 queues, 0 to 5 because S is 5. So that's our sum. And of course we're going to use bit vectors. Why? Because they give us a lot of properties that allow us to access things really fast. So I'm just going to have an array of them. I'm going to call them arm maps. So don't worry too much about the variable names. As we go along, I'll remind you of these things. So the key thing I want you to remember, though, is each queue is going to represent the sequences that add to a particular number. So say, for example, q sub I, or maybe like q sub 3. If it was q sub 3, so this is just an array of queues, Q sub 3, all the sequences as of generating them, if it's in Q sub 3, that means all the sequences add to 3 in that given Q. So as we build them, we want to get, our goal is to get to Q sub S, which will contain all of the ones that add to S. So you can think of this kind of like you're climbing up a ladder. Except the ladders are diagonal. And they work their way to the right. So let's just talk about a little bit of construction here. So the first thing is we're going to convert each one of these restricted sets to a bit vector. So it's an array of bit vectors. So say each one of these positions will correspond to a 1 if it's in that given set. So should be very familiar with this kind of idea. So for example, if I have, say, this would be the 6th position. If I'm only allowed to use 0 and 4, that would be 0, that would be 4. So all I'm doing is doing a simple translation here. So we have this other variable that's kicking around called clear till. Now, oftentimes, this is the one that tends to confuse some people, so listen very carefully about this one. So I said that Q sub S contains all of the valid integer sequences as we build these. We'll see how we're going to build them. Clear till's job is to prevent integer sequences from entering into Q sub S when it's not ready to. Now, what does that mean? Well, think of it this way. If you're trying to add up to a number, say S or 5 or 2, you have to keep in mind that maybe the 4th or 5th position isn't allowed to be a 0. Because remember, we're allowed to pick anything in these bins. It could be a 0, it could be a 1, it could be like a 2. It may not even have a 0 in it. So we need to find out the last position in these bit vectors where a 0 isn't allowed. Why? Because we can't put anything into Q sub 5 because as we're building these things in rounds, anything that's sitting in Q sub 5 just sits there in an array and everything else will just be zeros in the rest of the sequence. So as we build, each position in a round will be built, but once you get to Q sub S, we don't touch it. But there's going to be a position here where we're not allowed to use a 0 because the bit isn't set here. So we can't put anything in there because they're all just going to be invalidated immediately in the next round. Does that make sense to everybody? So just look up here. Say the 5th position here. It's not allowed to have a 0 here. So would there be any sequence that would be able to get through if they were able to get up to this point and allow it to be a 0? Say if I put, say, a sequence at this point and it adds to 5, and say it's still in Q sub S right about here. Is it allowed to have in position 5 a 0? No, right? So we can't have those. So we need some way of foolproof method to make sure nothing is going to be in Q sub S that we don't want it. So that's what clear till's job is. All you do is just do a linear scan of the first bit here until you encounter where the 0 may be present in that first position. And you just set it to the 1 right after. So that just indicates the round when you're allowed to put sequences into Q sub S. Otherwise, you just get rid of them. So just for example, remember that this particular one is 3. So remember the number 3. I know it's a lot of burden for you. Just remember 3. Just don't write it on your summary. Just don't say 3. That's the summary. Just don't do that one. But anyways, there are 2 trivial cases. These are very simple, exhaustive techniques. If it's just length 1, you just check the bit vector at the first position. If it's allowed in, you just let it in. It's very simple. If you have 2, you only have 2 positions in these sequences. So you just go through the pairs. N squared, right? You just take the pairs. So now I want to look at the main cases here. So this is when n is bigger than 2. So this is the first picture here. So we have something called a base step. So after the base step, we'll have something called a construction step, and then we'll have lastly an induction step. So the base step's job is just to think of like having cute puppies. We're putting them in boxes, and those puppies are going to turn into big dogs. That's kind of what you could think of them like. So if the bit vector in the first position says I'm allowed to put in that given element, I throw it into a queue. You just start at the left, work your way to the right. Remember, each one of these represents the sum at that given point for a sequence. So for example, remember in the first position, we're allowed to put a 0, a 1, or a 2, or a 3. So in our example, you'd be allowed to put a 0, you'd be allowed to put a 1, and of course you're allowed to put in a 3. But there's one little thing that I'll have to keep in mind a little bit too. So you just throw these into the queues, just enter them all in, and of course they'll represent those sums. So they're the little puppies now. So just don't worry too much about what we see up here. This is really just a construction of a graph. So just look at this picture here. So what we're going to do in the induction step is we're going to be turning those puppies into big dogs, really big ones. So we're going to take them. So whenever we're allowed to go to a next position, you leave the queue with that given sequence, you copy, make a copy, append the symbol that you're allowed to put in, then you enter it into the queue that it's allowed to be in after you add those two numbers in. So for example, if I have, say right now I have the 1, a 0, 1, and a 2, I'll talk about 3 in a sec. That would mean that in the first position, second position here, where the induction step starts, I'm allowed to put 1, 3, and 5. So 1, 3s, and 5s here. So that would mean if I have a 0, a sequence in Q sub 0, I just look at my graph and it says, okay, if there's an edge that allows me to put a 0 in, then I just well, I don't have one here, so instead I go to a 1. I see, hey, look, I can put a 1 in, so I take the sequence that it starts with a sum of 0, I put in position at that given round, that number, say 1, and you just throw it in where the sum would become. So it would be thrown into Q sub 1. So the base step is just putting the puppies in the boxes. In the construction step, you're just building these edge sets. And these edge sets, each round will have an edge set. So all you do is you look at the bit vectors, and you're just going to perform a little offset. So for example, you'll notice something here actually. So this is actually the second position you're allowed to put in. Notice it says 1, 3, and where's 5 here? Now, one thing to keep in mind is that we have this thing called clear till. Clear till was 3. You start at round 1. If you can't do that until round 3, you don't include anything that'll put you into Q sub S. So that's what this statement right here actually is. So that's the one that's going to make sure nothing sticks into Q sub S. So that's why you'll notice that none of these guys will go into Q sub S, which is right there. So don't worry too much about this. I'm going to show you a picture that will make it a lot more clear. So what you do in the construction step, you just take the linked list that you have, you convert them into a 3-dimensional array. Yes, I know, I'm going that far. 3-dimensional array. And then we use it for something called the induction step. So we have main rounds, then we have a final round for this. So if there was an edge in this, we take the sequence, so we go between all these queues. The key thing to remember is that you start at the right, work your way to the left, you leave a sequence out of that queue, you make copies for any edge that you encounter. So keep in mind there will not be any redundant ones in this, because we've got rid of those in those edge sets. So when we make a copy, we just simply put it in where it may belong, wherever, say if this were a colored edge, like say maybe this green one represents, I don't know, that one. That would mean that, that you're copying and entering them into a queue. Now note that these queues are the same. I'm just showing you a picture here to make it a little easier. Why? Because these are actually just the same queue. The trick here is you start from right to left. Right to left. It's a very fun trick if you're familiar with the in-place quicksort, where you just do things in reverse. So you can do it all in place. So if you didn't have this, you'd have 2 sets of queues. We'll come back to that, actually. So all it's happening is so really for our sake, just remember that in these, there's sequences. Each one adds to a number. And when we pull out each sequence, you copy it, append the symbol or number that you're interested in, that corresponds to an edge in an edge set, you enter it in. Very simple. It's just iterative. It's very, very iterative, though. You'll find that iteration there will make it very nice and easy to parallelize. But we'll have to do some more. So the last thing we have to keep in mind is the final round. This is the last one. Now, one property of integer compositions is since we're adding to a number s that we know predetermined, if you have n minus 1 of n positions, do you really need to do an extra round if you have n minus 1 of the numbers and they add to some number? Do you need to really do that extra work to get the last one? Probably not, right? Because remember, it adds to a number. So those first n minus 1 positions, they'll add to a number. Well, you just take the difference of s minus that. And you can perform a little check to make sure that it sits in. So you just sit this inside of that little check, and you just throw them all into q sub s if they're still valid. So don't worry too much about the deep parts of this. Just keep in mind that it's exhaustive, and we're just trying to get everything into q sub s. So when you're done, everything that's valid is going to sit in q sub s, and you just print it. Just print all the sequences in q sub s. So what we're going to do, so first off, does everybody get the big picture? So don't worry too much about the very, very fine details, like the edge sets. Don't worry about that, because when we're talking about the parallel aspects of this, we're not going to really worry too much about that. That's just more of a technicality. Key thing to remember is that there's these Q's, they represent some sum. We're going to leave sequences from one, and then they're going to go into another. Okay, so now I want to streamline this algorithm. You'll notice something that's a little bit interesting about the structure. It'll store all the ones that add to a particular number. Now, if I want to parallelize this, it causes a data dependency on the variable s. Does anybody see that? So notice that the Q data structure is here, so this collection here depends on s. But we want to parallelize this algorithm. We don't want s there. We want something to tell us about the number of threads, say if we're talking about shared memory machines, or an OpenMP here. So when we're looking at this, this is how we have the setup right now. Each one of these arrays or sequences has n positions. They tell you what it has, and they're sitting inside of something called q sub I. Now, what we want to do is we can take a very, very simple augmentation here. Just put another position in, put I there instead. So now you have the sum along the way. Do you really need s plus 1 q's anymore if you're able to store the sum internally on every sequence? Not anymore. You will not need that extra structure. So now instead you just have one orc big Q. So that's the big difference here. So notice that all we have now is you just have an extra position, and now all of these will satisfy this. So are there any questions about this little modification we did? So all I did was just take and just add a little bit of information to each sequence. So now all I have to do, if I ever want to print these out, just print the first n positions, and then just don't care about I anymore when you're doing the output. So one thing that we lose in this process is now we can't do this right to left thing. Now we can't do this all in place anymore, because we're losing some bits of information in the process. Because what happens is, as you go through each of these, you'll leave the sequences and you move to the left. You leave the sequences, you copy those sequences, you move them over. Note that this one's never really touched. Only things enter q sub s. But these guys, when you leave a sequence, you make a copy, you put it into whatever it may be, say q sub s. In the induction step, you'll see that things will actually be entering in these sequences as we do this process. Because remember, these are just the same sets of Qs. I'm just showing you two of them. So as things leave one, they can enter one. Now, notice that some of these can enter into themselves because they're appending a 0. So the sum doesn't change. So notice that you'd have to keep a counter around. It gets a lot more technical than it needs to be. But for our circuit purposes, we're going to have two sets of Qs instead. We'll see why. So just going to call them Q sub 0, 0, and Q sub 1, 0. So just call them 0 and 1. That's often how I'll just refer to them. So that's the first thing we're going to do, the streamline it. So now I only have two Qs now, and now they perform this procedure. And they just use the edge set exactly how we did it before, except now instead of referring to I in a Q, now everyone will have their own little bit of information now. Makes it a lot easier to do this. So we're going to call that a workbench. So there's our two Qs right there. Notice that this is actually a three-dimensional array, technically. So we're going to have another Q. We're going to call QF. So notice that we need somewhere to put all of these finished sequences. We're going to call it QF. We'll call it the finished Q. So Q sub S is equivalent as QF. So there's just one little technicality. Don't worry too much about this. You have to just do an extra check with ClearTill when you do the first step of this, because the original algorithm had more information you can do. You can clear the whole contents of a queue with one quick little swap, because you can know how much is in based on how much they're ordered by sum. So remember, there was like Q sub 2, all the sequences add to 2. It gave you a bit of information about all those sequences. We lost that by doing this. Now we have no way unless we check all of them. So we just had to add this little bit of information. Just don't worry too much about that. So we just use the same algorithm we did before. Now we just have a simpler structure. Now, let's talk about the parallel algorithm. So we're just going to be using the PCAM model here. So we're going to be setting up our algorithm. We're going to need two things. But our goals here are to have no data dependencies. We already did that. We took care of that. But we want to make sure we exploit as many threads as we're given. Second thing, we want to still keep this round-based structure, but we want things to be lock-free. That means there are no, in terms of OpenMP, there'll be no critical sections. None whatsoever. I do not want those. Why? Because it causes a burden on communication, right? So I don't want that. Third, I need a self-balancing system. So I'm going to be using a modification of round robin to take care of that. So we're going to be using a little mechanism to do that, and I'll show you it. It's actually not that complicated. So it should be simple. We want to design this so it works general purpose. So small number of threads is perfectly fine. So I want that speed up to occur with a small number of threads. So how is this going to work? Now all I've done is I've taken my workbench, and now instead of having just 1 and 1 in my workbench, now I have T by T here, T by T there, where T is the number of threads. So now instead of just having 1 by 1s on each one, now I've extended each to be like a matrix. So now it's T by T. So now I have 2D arrays embedded inside of here. So now each one of these is a queue. I bet you can see already one thing that's kind of going to come and con back at us. Notice that that's a lot of queues. So we'll be using this in a clever way. And also we're going to have T-finished queues. Why? Because each thread we want each one of these guys to have the ability to throw valid sequences in without touching one another in terms of memory. So we want to distribute the data in a manner so that we don't get this memory entanglement. So what are we going to do? So we want to first exploit loops. Probably the easiest thing you could do. In OpenMP, you just think, okay, I see a loop, I'm just going to carefully parallelize that sucker. So you can do that with the base step. So the one thing you have to keep in mind that this one needs a critical section. Though. This one needs it. The induction step, we're going to find, doesn't need it. So why? Because you're going to use round robin on the first set here, and you're just going to go on the first column and do this. So every time you enter now, you'll have this variable called distribution, and you're going to be incrementing it by 1 on each enter operation. When you make a copy, you enter it, increase distribution. Problem is, all the threads want dibs on distribution sub 0 in the base step, so we need a critical section. Construction step, dead easy. Just throw some commands on that sucker. Very easy. Now, this is effectively the lock-free construction. So, nice and simple. Now, it doesn't look very simple down here, but I'll explain. So, each time you leave a sequence, what you want to do is each row is going to match up with a column. So, on an odd round, say round 1, round 3, round 5, what you're going to do is you're going to leave queues from here. So you're just going to go through your left to right, doesn't matter what order. Get rid of those sequences, enter them in on the column that corresponds to them on the opposing side. So you just iterate this right here using a distribution variable that's allocated to that thread. So each thread will have its own distribution. So it's just an array. So you just go through these, perform the same thing I just showed you in the base step, do round robin on the column. Do that for each row, and then each corresponds with a column. Likewise, on the even round, you'll notice that now I'm on the right side. So every single time I go and put something on that side, the opposing round will take things from this side and bring them on over here. Using, well, it's another round robin over here. So it's no different. It's just I'm going back and forth. Now, does anybody see why I'm doing this? Anybody see why? Think of it like if I had a pool of, like say if I have a bathtub. If I start pouring water into it in a particular way, say maybe I swipe it like this, down through the middle of the bathtub, not like slice through, but the key thing here is if I do that, the water spreads, right? So what I want to do is you can think of this kind of like I'm taking the water, dumping it into the bathtub, and as it goes down, splashes like that. So I'm doing this with now T buckets going splash, so it's going to be spreading out. So I'm spreading out the sequences by doing this. So now you can see where I'm going to go with this. So let's go down and break down the PCAM here. So partitioning, this is coarse grain. We're going to be doing whole operations on queues. Very coarse. So that can be very expensive, but we're trying to break it down into a primitive task that's just simply taking these copies, leaving them from a queue, entering them into these opposing queues on the workbench. Just in that manner. Communication, the only bit of communication you have to really worry about, aside from the forks and the joins, just at the end of the induction steps. We don't want any intermingling between these even and odd rounds. So they have to perform the synchronization at the end of each induction step. But inside of there, it's lock-free. No critical sections. So they can just do their own thing. So agglomeration, very easy. Each one of these Q sub Fs will contain valid sequences. So I just assign a thread, whether it be the main master thread, or it could be any other one, or all of them at the same time if I like, and just print them. That's all I need to do. And mapping, all you have to do, very simple. Since we have a T by T matrix on both of these, just give each thread one row, or one column. So each one of those matches up nicely, so the mapping is really straightforward. So you can see that this nicely goes along with exploiting a loop. So just some quick things I'm just going to point out here is if you ever want to prove that this algorithm works, you can do so by induction. Now one clever little technique is using a reduction. So if you take this, say this is your workbench right here, notice that all I did was increase the number of queues by T by T. So if you ever want to prove the correctness of this algorithm, all you do is you take the T by T, turn it into a 1 by 1 on each. You can show that the sequences are identical inside of there, and you can induct on the dimension of both these matrices here. So that's how the induction would work to prove the correctness here. So you can first show that the streamline one works, which is not that hard. You just relabel things, and then you just reduce it by what I just described, and you just do the induction step, which is very simple. You just add a row and a column. Makes it very easy. So note that the absolute speed up of this algorithm is T, but we'll find out that it's not going to work that nicely. So we're going to find out, I did a little bit of experimentation here, so quick things I want to point out is that I use absolute error to measure the load balancing. So what exactly is valg? So if I look at my queues that are allocated to threads, I can look at how many sequences are in there versus how many I should have. Now, in my experiments, I use weak compositions. Why? Because I can use a lot of nasty choose functions to predict how many there are going to be in there. So all I do is just divide it by the number I want in there. So I just divide the size, divide it by the number, and that's all I need to break down and get an expected number versus what I get in the algorithm. So when I use this, so note I did use this on helium. How many of you have been tinkering around on helium? It's fun. I don't know how much memory I sucked out of that thing when I was doing these. But yeah, they're fun. But yeah, so these are some of my experimental results. So note that I did some cases on varying different kinds of sub-instances. So like say the Fibonacci sequence, if you want to make ones with all that satisfy the Fibonacci sequence. Or if I want to look at ones with powers of 2s only for the values. Or I want the weak compositions. The reason why I chose these is because these sets monotonically increase based on N and S. So there's none of this unpredictability with the size of the sets. Why? Because if you restrict your numbers to only specific values, you'll lose a lot of the cardinality of the set. Shrinks a lot. So weak compositions, they're really nice for this experimentation because we can test how much we can put on and test how well we can balance things out. So what I have here is I've laid out what I have here from my experiment here. I did 8 threads. So no, I went up to 16, got the same kind of results. So if you look at this number, so the sum is allowed to be up to 20, have length 12, that's over 84 million sequences. That's a lot. So what you do is you just look at each one of your rounds, so each one of those that puts one position in, and you can see that the average of this calculation, in terms of percent, is decreasing over time. Why? Because we're using round robin, but we're using round robin in a creative way that shares it amongst all the threads without needing to lock up and use critical sections. So it's a little clever use of this. So no, this is just showing you what I have up here, and this is a nice stack chart. There's not too many times where you get to use a stack chart in a more useful way. Sometimes you're pretty discouraged unless you can find a nice way like this. So some other things, just speed up. So as I said, the theoretic speed up is T. Why? Because you're breaking it down asymptotically down into even-sized amounts for each Q to work on. But the problem is when we do this, we get about 2.37 as its peak. But notice the number of threads we need is not that many to get the speed up, which is what we wanted, right? Very general purpose, very easy. But the key thing here, also I want to point out, this is 90 million, almost 91 million sequences used on this experiment. That's a big number. Well, at least in this domain. It could be even bigger if we wanted to. So the saturation will occur a lot quicker. Why? Because the size of the sets get rather large, but another problem creeps in. Though log-free, you get an exponential amount of accesses to global memory. So remember, in a shared memory machine, we have global memory. All this stuff's being stored in global memory. So I already said the size of the set's exponential. So we're going to be getting an exponential number of data accesses, which can be costly if, let's say, the bus of the machine is small. So note that if you ever want to take advantage of the speed up, of course, we can take enter at this law and increase N or S to get back the speed up that we want. So we got pretty much what we were looking for, but also note there's a little bit of overhead. It works very well. So just as some notes, just keep in mind that we've looked at a lot of variety here, but the big thing here is that we've gotten down to a parallel algorithm that's relatively easy once we've streamlined and done all that work to put it together. So thank you very much.